Hello, everyone. Hey, guys, can you hear me okay? Hmm. 1 second. I don't think my mic is working. All right, how about now? Can you guys hear me okay? Testing, guys. This is working. Oh, okay, I'm sorry. Okay, there we go. Now you guys can hear me. Thank you. Hello, guys. Welcome. So we are going to get started. Let's see. Okay, yeah, we got pretty good job. So, all right, guys. So, quick review of last week's assignments, and then we are going to go from go look at the coverage today, right? Excuse me. Let me share my screen here. So I cut down my screen resolution. Let me know if this is better. Can you, because I heard comments that my previous screen was just too small. Hopefully this one, we should be able to be reasonably better, I'm guessing. All right, guys, so where are we on the overall guiding? So last week was intro to machine learning. We did a little bit of theory, and also we looked at scikit, right? And the scikit was exercise for you guys to kind of play around with scikit and get familiar. We are going to use scikit more and more, right? So what I want to start by doing a quick review of last week's solutions. So again, the solution file is shared with you guys. If you go to the guide of machine learning, the class submission folder is now open. Go ahead. And so I'm going to actually highlight, I'm going to go through Cynthia's solution. Cynthia, I'm not sure if you're here, but yes, I just looked at it. Looks good, so I'm going to demo that, right? So very good. You can.
Yes, I am here. The thing is, I have a feeling I didn't answer everything. I feel like I didn't answer everything.
That's okay. That's perfectly okay, right? Yeah, and I saw some of you, and I sort of added some of my as well. So I'll walk through that all, right? So don't worry. So it doesn't need to be a perfect solution. So, but thank you for submitting it all. Yeah. All right, guys, so you can look at the solutions file. Again, how do you get the solution file, right? Basically, right, you guys know this by now, right? So go to the welcome page and look at the weekly assignments. And then that's where it is, right? So we were at week 7 last week. So scikit, right? I had you to look at scikit. And submission folders here. So click on it, so you simply double click on it and you simply say open with Colab, and that's it. Very easy. So I have already opened. By the way, when you open with Colab, I recommend you guys make a copy of this, right? Because otherwise any changes you make may not be saved, right? Because you're looking at it in a read-only view. So this is a good habit to develop when you look at somebody's notebook on Colab. Basically, make a copy. Just make it a conscious, right? All right. So, all right, so scikit-learn. Couple of things I want you guys to play around with. One is loading the built-in data set. And the other one is making your own synthetic data, right? So, so here's data sets. So, and here we are loading iris, right? So let me go ahead and just print iris, right? And when look at this, where's this? Okay, okay, right? I kind of see a bunch of numbers. All right, that's interesting. But what does the numbers mean? To do this, each data set will have a description column, right? So you can sort of see here, right? It's kind of hard to see in this Colab, like when you scroll down, because there's this double scroll bar, which I really hate, right? So they have, a description field, right? It's kind of hard to read, right? Because, it's kind of all kind of bundled into one. So usually what I do is I can just print out the description separately, right? And then let me comment this out because this just takes too long, right? And here you get an idea of the data set. And this is pretty common attributes. You say, okay, what does the data set mean, right? All that. Does that make sense, guys? Let me try something real quick. Let's see if this works. And then, pprint is basically stands for pretty print. Let me see if that makes the display a little better. Let me try this out. Oh, there you go. It does. Okay, good. So, so this is much nicer, right? So you can sort of see here, right? It's printing out the original, the actual data. There we go, right? See print the description. So it says, okay, what does the description mean, right? And then what are the columns, and basically all about the data set, right? And then actual data. So you'll see like a few columns, and this is something worth remembering, right? You'll see each data set. You'll see a description column, right? Also for each data, actual data is like this data, right? And see, data is basically simply array of numbers, right? And then if you scroll down, you will see what are the feature names, meaning, what are the names of the columns? Yeah, okay. So these are pretty common attributes. It's good to know. Feature names, and then data.target, right? These are very common names, and if you look at this, most of the data sets will kind of adhere to these kind of convention, right? Which is great. Okay. Now, all right. So I look at the data. Okay, sure. I see the description. I see a bunch of numbers. That's great, right? These are remember, these are all pre-built data sets, right? Meaning it's already packaged with scikit, so I don't have to do any loading or anything, right? And also use the target names. That's good. Okay, so let me put that too. That's good to understand. Target names. Right. That's it, right? Now I look at this. Okay, just a bunch of numbers. Okay, that's fine. But I want to understand a little better. So usually what I do is I convert them to pandas, and this is pretty standard snippet, right? So let me kind of put this back here, right? Load iris. Actually, let me do all that. So here's what I usually do, right? So I import, right? I import my scikit-learn, iris, iris load iris, and then I import my pandas. So I'm creating a pandas data frame, right? Iris data frame equal pandas.data frame. First part is data, and that's always iris, whatever the data set is data, and the name of the columns. Column names is iris feature names. Remember feature names, right? There's an attribute to this. And I simply print this out. And if you look at this, this is much nicer. Right? Now I sort of see a pandas data frame, and I see, what the columns are, and it's a nice display, right? Anyway, so you kind of make it a habit. You can always convert an iris, not iris, I mean, scikit data into a data frame, and which usually kind of a much nicer experience. So let's do for Boston, right? Same thing, right? So let's say, okay, same thing, right? Iris, data set load Boston, right? I don't even know what data sets are, so I'm simply saying data frame, pandas data frame, Boston.data. Remember, data is the actual data column, and then data Boston.feature names. That's it. Display, you see all the data. Pretty neat, right? And if you really want to know what this means, then you can sort of go and say, you can do a print, right? You can say, okay, let me see what data set, what does this mean? You simply say print Boston description. That's it, right? And you get all of them, right? You say, okay, what does CRIM mean, right? Okay, sure, CRIM mean, right? Per capita crime, right? So anyway, right? So data is built in and already cleaned up, right? And we sort of see all that. Pretty good, right? Any questions, guys, on this one? So these are built-in data sets, and these are pretty handy because when practicing machine learning, sometimes you just want to have a clean data set to practice. And because and as we'll see, right, when you load real-world data set, you'll spend a lot of time cleaning up and massaging the data. But sometimes you just want to just get some good data and get the algorithm working, right? And that's why the built-in data sets are really great. Mm-hmm. All right, guys, any questions on this one? All right, so that's loading the data sets. Now, Scikit got another cool thing. It has something called synthetic data sets, right? So in the same dataset package, they have this make functions, right? So let me do one real quick. Let me do a regression test here. So I can say sklearn. So we can say sure sklearn data sets make regression, I think. Sorry, 1 second. Give me one moment to check something real quick. I just did this yesterday, so I want to make sure I have this set up. One moment, guys. All right. Good. All right, that's what I'm looking for. Thank you. Sometimes it's easier to Google than trying to find your own work. So, all right. So we're going to make a regression, and I think first thing is number of samples and features. Okay, right? So that's good. So, and samples, say 100 samples, and features, let's just say 1 for now. All right. So the way the algorithm is, it returns X and Y, right? So when you make the data, pretty much the syntax is it returns X and Y. So you can say X and Y, right? Now I'll explain why something, right? And then you say same, you say print X and then print Y. Let's try this, should work. All right, so X is a bunch of numbers, right? Y is another bunch of numbers, right? Now, like I said, if you just look at the numbers, it doesn't really mean much. So let's not do this. Let's actually do a graph. So you get a plot example. So we're going to say plot, scatter, and I'm going to say X comma Y. And I'm going to say plot.show. Remember, we are trying to figure out a regression example, right? There you go. Cool, right? So I can say make regression. So what it does is it basically goes and makes me some synthetic data. When I say synthetic, meaning artificial data, right? It's generated. And I say how many data points I need, right? 100 data points, and how many features. So in this case, just one feature, right? This way I can graph it. And another thing you can do is, this is a pretty straight line, right? And it's kind of boring. So what you can do is you can add noise. Yeah, noise. Okay, so let's add some noise to make this a little bit more interesting. Because real world data is not going to be, let's say noise 3. Let's see if this works. There you go, right? So now you sort of see the data is kind of, right? It adds a little bit of noise extra. And if you sort of increase this, you'll see our data points kind of, getting more, more scattered, right? You get the idea, right? And this is something you can tweak. Now, why does it matter? Because this way I can generate a quick regression data point without having to, go, hunt for data. So in all of our algorithms, our first assignment I will ask you guys is just use the make regression, make classification functions, just to get some sample data so we can get going quickly. So that can make sense, guys. So basically, they are like all under make underscore something, right? Make regression, make blobs, make right in there has like this, make blobs and make classification, right? All this, and they are pretty much the same number of parameters. Right?
So one question. So when we say the features equal to 1, so actually which feature it is actually selecting for doing the regression?
Oh, it's generating a bunch of numbers randomly, right? So we are kind of generating like X and Y graph, right? And you will sort of see, right? I mean, it's kind of generates data like around like zero centered. Remember, like and you guys then studied this the other day. Remember, they kind of do like a normalized form, right? Yeah, like zero centered here, zero centered here.
Yeah.
Yeah, that's it. So don't try to interpret this data, right? Because remember, this is just some random data. The only thing they are doing is they are giving you like some clean data. Like for example, so it can almost feel like a straight line, right? Because if you make if you make the noise 0, it'll basically fit in a straight line, right? And you can sort of increase the noise a little bit just to kind of make the data a little bit noisy, and then you sort of see that the points kind of move around a bit. So again, so just imagine they are generating random data for us to do regression on, right? That's it. Yeah.
Okay. Yeah. Thank you.
Right. Now, so why do we care? I mean, we all know this is artificial data, right? This is, right? The reason this is nice is basically, I can actually get data and then I can actually kind of try my algorithms, right? Without having to worry about, loading data, cleaning data, the whole thing you guys have been doing, in the last few weeks, right? So that's it. So this is a very quick way to get going. Okay. All right. Make regression. So the next one, Cynthia did, is make blobs, right? So this is pretty cool. So you can say blobs, like how many samples do you need? How many features do you need? And centers basically meaning, just 2 centers, right? So if you look at that, if you plot the data and you see 2 blobs, right? Now, why do we use it for? We use it for doing like classification. For example, so let's say you're running a classification and we are gonna look at this algorithms today. Like, can you like draw a line that kind of, like for example, annotate, right? For example, can you draw a line that kind of divides the data cleanly? I mean, I didn't do a good job, right? You can see like a one brown point over there, right? Meaning, can you separate the data cleanly? So yeah, right. So all these things, we'll come, we'll look at the coming weeks. Okay, make blobs, make classification, same thing, right? You can sort of see here, right? Right. Again, you can play around with these things and you can sort of tweak this, tweak these numbers, right? And kind of play around with this one, right? And you can see, this is a nice cluster, right? All right, guys, so this is synthetic data. Okay, so and we'll be using these more and more. Okay? Now, the other one is training, testing, split. Now, why do we need to split the data, training and testing, right? This is interesting. So I want to quickly do this real quickly with you guys. Let me explain this, why we need training and testing. You guys have the slides already. I'm going to be jumping around a little bit just to sort of save some time. Right. So let's say I built a model, right? And sorry, let me start here. Right. And this is sort of a machine learning sort of a loop, right? We collect data, clean data, right? Which we have all done, exploring data, feature extraction. Again, all of this we have done already, right? So let's say next step is I'm going to build a model. So let's say we built this model, right? And we will look at this in detail later, but let's say we actually built a model. How do we test my model, right? So that's called model evaluation, right? How do I know my model is correct or accurate? So for that, right, think of it like this, right? Imagine you are doing, you're writing code and you're writing unit tests. So you write your code, right? Usually somebody else writes the tests, right? Unit tests. And when you run the code against a unit test, you actually get results, right? Same thing in machine learning. We write our algorithm, right? Remember, algorithm plus data, which gives us a model, right? Remember, we talked about all the terminology last time. Now I have a model. I need to test the model. Yeah. So by the way, is the audio still alive? I hear some people are, lost the audio. Can you guys still hear me? Yeah. Let me know in the chat window, guys. Yeah, if you can still hear me. Okay, good. All right, good. Thank you. So I create a model. So imagine your model is like a code. Now I need to test my code. So just like my, think like running JUnits or whatever, we're going to test our model, and we are going to basically, basically give it a score, right? For example, remember when you're running a JUnit test on your code, let's say you ran 100 tests, and the code passed like 85. So you can say, okay, the code actually is 85% accurate, right? Because it failed the other tests. Same thing, right? In the model, we ran 100 tests. If it passed the 85 test, we'll say the score is 85% accuracy, right? Okay. Now, to do this, so let's say I'm giving you, say, 1,000 data points. And I say, go build a model. And let's say you used all 1,000 data points to build the model, to train the model, right? So when the model is trained, so we train, model actually has seen 1,000 data points. Now, if you use the same data, same 1,000 data points for testing, what's going to happen, right? The model could cheat by memorizing the data. Remember, because during the training time, model has seen the input and the expected output, right? So the idea here is model is learning. It's kind of self-adjusting to produce given the input to given the expected output. So it actually seen the data, right? But when I use the exact same training data for testing, the model can cheat. And so there's no telling if the model actually learned something, or the model simply memorized the data and it's gonna give me the answer, right? So imagine I'm there's gonna test at the end of this class, and I'm giving you guys some sample questions. And in the test, I give you the exact same sample questions. So you don't really need to understand the question. You can simply memorize the sample question and the sample answers, and you can score pretty well on the test, right? Because you simply memorize the sample questions. We don't want that to happen in machine learning, right? So what we do is we split the data, right? So let's say I have 1,000 samples. We split the data into 2 sets, one for training, one for testing, right? So typically, I'm showing you like a 80-20 split. So for example, 80% is reserved for training and 20% reserved for testing. Because we still want to give a lot of data for training, remember? Because, because the more data model sees, the better the model gets. So that's why we say 80, right? We don't do like 50-50 split, because then what you're doing is you're taking away too much data from training. So 80-20 is a good split. I've seen people do 70-30. I mean, there's not like a hard number. You can start from one of these and then kind of adjust these up and down, right? Based on your needs. So let's say 80-20, right? So I have 80% data for training. So the model's only trained on the 800 samples. Now the other 200 samples, the model has not seen. We are keeping it away from the model, right? And then for testing, that's what we use. So it's like, same example, like let's say there's gonna be a quiz at the end of the class. I'm giving you some sample quiz, right? So you can understand what the question is going to be. But for my testing, I'm not going to give you this same question. I'm going to give you different questions. So I'm actually testing your knowledge rather than whether you memorize the sample question. See what I'm saying, right? So that's why it's very important. And I see this mistake a lot of the time especially when people new to machine learning, they will use the entire data to train, and also they will use the entire data for testing, and the model will rate very high. They'll say, oh, 97% accuracy. Like, woohoo, right? That's great, right? But when they deploy the model on the real world data, meaning like, when you deploy the model, now the model is going to see new data it hasn't seen before, right? It'll do pretty badly. Does that make sense, guys? Yeah. So that's why it's very important to do like train test split. Any question on this one, guys? Does that make sense why we split the data, training and testing?
Yeah, one question is if the data consists of both actual data and synthetic data, so can we apply the similar approach, or we need to go in a different route? Actually,
yeah, you can pretty much use the same same approach, right? Because data is data, whether it's actually real data or synthetic data, right? The process is still the same. Yeah.
Oh, okay.
Yeah. There are some corner cases, but I mean, let's not get into them. I'll highlight in some of the labs, we will do later. But yeah, for the most part, follow the same process. Because if you follow this process, you're already ahead of a lot of people, because a lot of people just use the exact same data for training and testing, right? Which is a bad deal. So, all right, guys. So, let's say, okay. So there's one more thing I want to cover, and then we'll move on. Just kind of, we did the training and testing. So now the question you're going to ask me is, okay, so I'm choosing 80% of the data. How is the 80% chosen? It's random, right? So in machine learning, what we do is we take random samples. So I'm telling the algorithm, okay, go, from 1,000, pick 80% of the data randomly. So 800 samples randomly, right? So then the remainder is testing, right? Now, if you think about this, every time you do this, you'll get different data sets, right? Because you're picking randomly. So, and this is kind of error prone, because sometimes we do, you get lucky and you get a pretty good training set. So the training set covers all the use cases, right? Also, if you're lucky, your test questions will be easy test questions, right? So you will do pretty well, right? Because why? Because we are doing random, right? But if you're not lucky, sometimes when you select the test training data, your training data may not be all that representative. So your model doesn't really learn well, right? On the other hand, you can probably get a hard test set, right? It's kind of like exam, right? It's like, imagine, your test questions, sample questions are, kind of weak, right? So you're kind of not learning much, but then, but your test is very hard. So of course you're going to falter, right? So, and just by randomness of the whole thing. Now, how do we fix this? And the way to fix this is basically something called cross-validation. And we'll talk about this later, but I want to show you guys very quickly what that means, right? So what it means is, right, we don't do one run, right? We do systematic runs. So for example, what we do is we divide the data into multiple segments. They're called folds, right? So here, let's say I have 10 segments. We keep one segment for testing and everything else is used for training, right? So this is fine, right? We understand this. Then the next run, what we do is we reserve another segment for training, right? For example, let's say this guy, right? The next example, this guy is reserved for testing and everything else is used for training. And the next run, next segment is reserved for testing and another, right? So you get the idea, right? So basically what we are doing is we are systematically running through the data, keeping one for testing and the rest for training. Does that make sense, guys, right? So the way we're going to visualize it like this. So imagine this is my data set. I split into 5 segments. Run 1, first segment is used as test data. Everything else is used for training the model. So that can give me more, give me one model 1. Next run, so remember we switch, right? Next one, let's say this guy becomes a test data. Everything is used for training. So now the training data is different, right? Because now if you look at the sets, training data has changed. So it's going to give me a different model. So I get a different model, I get a different accuracy, right? Remember, each model is going to give me a little bit of different accuracy, right? Because they're trained on different sets of data. So we keep repeating this, right? So I do 5 runs. Each run, we keep alternating the test set, right? And then we end up having 5 models. Each run gives me a different, slightly different model. Why? Because remember, even though the same algorithm, you take the same algorithm, run it through, different data sets, you get different models, right? Now these models have different varying accuracies. Now, if you say, okay, what's the best model here, right? You cannot really pick a best model here. Why? Because the same data, if you train the model using different training and testing data, you get different models. So usually what we do is we take an average as accuracy, right? So we have multiple models with the multiple accuracy. So you can say, okay, with this data, with this algorithm, I can achieve around like on average, you add them all up, and then get the average. Does that make sense, guys? Right? So and this whole process is called cross-validation, meaning what you're doing is you're training and testing, but you're not just doing one run, you're doing systematic runs, right? So, okay. So kind of the way you look at cross-validation is, imagine this, right? Imagine I'm asking you to solve a problem, Well, why the accuracies are different? Because each run, the training data is different. You see the training data keeps changing, right? So as you train your data with the train your algorithm with different data, you end up getting different models, and they're also being tested on different test data. So imagine I'm giving you a quiz. Everybody gets a different test questions. So now your scores are going to be different, right? So the reason we are doing this is because we want to get an understanding of the overall accuracy, right? We don't want to just do one run and say, okay, run 2, I get 84% accuracy. You know, that's not very meaningful, right? I want to do multiple runs and get an idea of the range of the accuracy.
Is it because the distribution of the training samples you've chosen must happen to be closer to the distribution of the test set?
Right, we would like it to be, right? But in real world, you know, that doesn't really always happen, right? So like what I see in the training data may not necessarily represent the test data, because there's always going to be some discrepancy, right? So, yeah. Mm-hmm.
Thank you.
Yeah. So yeah, so and yeah, right. So and this is again, you know, we just kind of started looking at this, guys. You know, we will look at this a lot more as we go, you know, as we go do the labs. How many runs we do? That's, you know, that typically, you know, people that do like, you know, 10 runs, 20 runs. There's no like a number. Typically, I recommend start with 10 runs, right? And then adjust the number of runs based on results, right? So yeah, so there's not like a correct answer for like how many runs do you need. Typically, people do like 10, 20 runs, right? Basically. You remember, each run you're doing is going to actually, you know, you're going to actually spend, you know, it's going to consume compute power, right? So the more runs you do, the more time you're spending training. Yeah. Mm-hmm. So
instead of splitting as it is done here, could it be? Could we take random samples 5 times?
Right. So then, you know, you could, but then, you know, the reason is then, you know, your experiment cannot be repeated, right? So let's say you take 5 random runs, right? And then you ask somebody else to repeat this. Nobody can repeat your result, because why? Because, you know, everything is random, right? So cross validation gives us reproducible results, because why? You're systematically testing, right? You're going through the entire data, testing systematically. That's a great question, right? Yeah, so the reason we are kind of doing this is, like, you can see like every part of the data has a chance to be a training set. Like, for example, let's take this, you know, this fold, right? This fold was used for training for a few runs, and also it was used for test for 1 run. So so we can systematically go through the data, so there's no data untouched. Does that make sense? If you did random run, there's a very high, you know, there's a very good probability that like 1 segment of the data was never used for training or never used for testing. So this is what we are doing. We are kind of bringing some order to randomness. Yeah. All right, so great questions. And accuracy we'll talk about a little later, right? So for right now, just assume like how many tests it passed. Like, for example, I gave 100 questions and my model answered 80 questions correctly. So the accuracy is 80%, right? So let's kind of go with this for now, and we'll come back to this one a little later. Okay. All right, I'm going to do one more and then we're going to wrap it up. All right. So typically what it runs is, in real world, let's say you want to solve a problem. There's more than one algorithm that's you know, that you can use. So which one do you guys use, right? So the answer is we use all and then kind of see which one works better. Right? So in machine learning is trial and error, right? So let's say in this problem I have 3 different algorithms I've shortlisted. I'm trying 3 different algorithms, A, B, C. And so I'm running them through cross-validation, right? So algorithm A basically scored from 60 to 72%. Remember when you do cross-validation, we get a range of, you know, range of accuracies, right? So algorithm A basically produce 60 to 72% accuracy. Yeah. Algorithm B gave us 70 to 85% accuracy. Remember, it's always going to be a range, right? And algorithm C gave us 50 to 90% accuracy. Now, question for you guys is, which one would we choose? Which algorithm do you guys think is a better fit for this problem? What do you guys think? Is C a good choice? Because, you know, C gave us 90% answer, right? As a matter of fact, C is not a good choice because sometimes C gives yes, C can give a high accuracy, but you can see it's very, very variable. Right? The accuracy range from 50 to 90%. It's a very wide gap. So what that tells me in machine learning terms is it's not a stable model. In machine learning terms, we call it high variance, meaning the accuracy varies quite a bit, right? So it's kind of a volatile model, right? So even though sometimes you can see it's giving us better results than everybody else, we don't usually choose this because it's just a volatile model. Now imagine this, right? Imagine if you just did like one random run and you by luck you got the 90% accuracy, and if you chose C algorithm, then you actually use the C algorithm next, in your actual production, it gives you 50% accuracy. And you're disappointed. You're like, what happened? Because during training, we got 90% accuracy. Why is the accuracy dropped to 50%? Because what you did, you basically just did like one random run and you got lucky and you got 90%. So it kind of gave you a false confidence. That's why cross-validation is very important, because cross-validation will basically systematically test the model and it'll give you a range of what the model can, is capable of. Right? All right, so we're eliminating C, right? You're saying, oh, yeah, right? C is too volatile. We don't want C. Now the choice between A and B, right? So looking at this, I look at the gap usually, like, okay, so it's like, A kind of, so around 12% gap, right? Lowest to highest. B is about like 15%. So, they're kind of in the ballpark, right? So not too bad. Because we don't want this gap to be too large either, like C, right? Because that, that leads to, unstable models. So I can say, overall, B seems to be a better performing algorithm because, right, overall, it does reasonably well. So is that gonna make sense, guys? This is how we use, select models by cross-validation. And in the labs coming up, I'm gonna ask you guys to say, okay, solve this problem. I'm not gonna tell you guys which algorithm to use. So each group will use a different algorithm, and right, because you'll find there's more than one algorithm that can solve the problem. And you're going to try them out, and you're going to figure out, okay, which algorithm is the best fit. And it's not always one algorithm. For example, maybe algorithm B worked in this case for this data. Maybe you have different data. Maybe algorithm A might be a better choice. Right? So it's very data dependent. So we never make statements like, oh, algorithm B is always the best choice because it always produces great results. Which algorithm works best is going to be for your own data. So what's important is we understand the concept, what's going on, and we also know how to actually do this in practice, right? So we can quickly evaluate algorithms and pick the best algorithm for us. Good, guys. So I'm gonna pause here for a minute and see if you guys have any questions, right? So what we looked at is basically how do we test the models, right? Right. So again, it's kind of a quick cap, right? So we don't do we don't reuse training as testing because that will lead to false confidence because the model can cheat. So we split the data, typically 80-20, 70-30, whatever, right? Whatever percentage, something along the lines. And it's a random split. So this is better than before, better than using all the data, but that still puts you at the mercy of randomness, right? Like I said, in some cases, you get very lucky and you get a really good training set. So your model learns a lot. Sometimes you're unlucky, you get a very bad training set and your model doesn't learn a lot. So kind of you're leaving things to luck of the draw, right? By the randomness. So to alleviate this, what we do is we do cross-validation. What we do is we systematically go through all the data, right? And then basically at the end of the cross-validation, I get like a range of accuracies, right? And then and then what we do is we run the cross-validation across many algorithms, and kind of see how the algorithms stack up against each other, and we can pick the best. Right? That's a quick summary, guys. Any questions on this one?
So based on this, we have 3 algorithms for one problem, 3 solutions. So from the best practice aspect, do we need to maintain like 2 algorithms always and keep cross-validating and take the best every time you do a data refresh?
Good question. So because which algorithm is going to be best is going to be mostly determined by your data, right? So when you're starting out, I recommend at least try 2 or 3 algorithms. And then after the first run, you may settle on say algorithm B, and then maybe you can just use it going forward. But when you're starting out, I would definitely recommend you guys at least try a few, right? To kind of because you get an idea of which one works best for you. But once you pick one, most likely that algorithm will be a good choice going forward, unless your data changes drastically, right? As long as your data is kind of a similar pattern, right? Whatever you chose from the first run will be valid. But if your data keeps changing, in a very unpredictable way, then I would recommend kind of, you want to kind of, keep a few algorithms around and then see which one works best for the current data. Yeah, right. So, great question. Anything else, guys, on this one? So we are kind of, starting to look at some of the machine learning concepts, right? So now when somebody says cross-validation, okay, yeah, you see, okay, yeah, I see, I understand what it is, right? And as you can imagine, there's a lot of math and stats behind this, guys, right? I mean, people have spent years getting PhDs in figuring out the best cross-validation approach. But, for us, the good thing is these are all implemented with us, with the best practices. We just want to be able to understand them and use them, right? And that's pretty easy now, right? As you can see, and I'll show you some code samples later on. All right, so I'll stop here. So let's go back to our lab. So this all basically came out, why do we need test and training split? So now you guys understand why do we need to split the data, right? Why we don't give the entire data for training. We have to split training and testing, right? So let me see one thing I want to look. I'm looking for a quick graphics. One moment. I can find it here. Right, so again, you guys probably recognize these, right? These graphs, right? These are all, the ones you guys been playing around with, right? So let me see. Sorry, I'm looking for a particular graph again. Just draw it. All right, no, I'll just draw it here. All right, guys. So another thing that confuses people is why do we need the training testing approach? So let me draw here, right? Give me one moment. Let me see if I can pull this up. There we go. Yep. That's what I was looking for. Okay, good. So you guys can see the screen, I hope. Okay. So the way we approached, test split, and once you understand this, it won't be mysterious, right? So one thing you will see is when you do the train test split, let me show the code here, right? You get 4 return values. And this confuses a lot of people. Here's why, it's very simple, right? So remember, this is my X and Y, right? What is X and Y? X is my input, Y is my output. So let's say I have 1,000 X, right? 1,000 data points. So I have 1,000 inputs and 1,000 outputs to try. So X could be something like, your housing data, like bedrooms, bathrooms, whatever, right? And Y could be the final sale price. So basically the idea is given X, you predict Y. Right? Now, what we are doing is we are splitting the data into, say, 80-20 split. So for training, I'm splitting from 1,000, 800, same thing, right? 800, right? So that's called X train and Y train. That's a training part. And then we are also doing testing, right? So remember, right? 800 for training, 200 for testing. 800 for training, 200 for testing. So kind of, if you imagine this, right? Imagine kind of, I have like an Excel spreadsheet, right? let's see if I had this one, right? Let's say this, I'll just use your example, right? Let's say this is my Excel spreadsheet of everybody attending this course, right? And I want to basically, let's say, split this into training testing. I can simply say, okay, right, right, okay, or just no, it's too small. Let's say I'll just pick first 20. I'm going to say, you know what, everybody up to here is my training, and then everybody after this, right, oops, right, everybody after this is testing. So what I'm doing is I'm simply like doing a doing like a just a simple grouping. Right? But in real world, we don't just do like sequential grouping, right? We actually pick randomly. We say so I'm going to say, okay, right, everybody here, 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 right? This is my training, right? And whoever's left is testing. So you just get the idea, right? So if you look at the training and testing, it's split randomly. Right? So for example, like for example, row number 0, right? So so row number 1, part of training. Row number 11, randomly training. Row number 22, randomly training, right? So that's what we split. So that's why when you give X and Y for splitting, you get 4 values back: X train, Y train, X test, Y test. Once you understand this, it'll make sense, right? So take a look at this code, right? Here's my original data frame, right? So let me do this here, right? Okay, so here's my data. Just simply creating a billing and tipping data, and then so actually, yeah. So, okay, here's my data frame, right? So here's what I'm doing is I'm actually creating X, and I'm extracting X as right. This is my input. So again, idea is given the bill amount, can you predict the tip amount, right? So X is basically going to be like, so you can say print X equal, it's going to be just bunch of numbers, right? Right, that's it. X is a bunch of numbers, right? Same thing for Y. Okay. Right, so you can say Y is the tip data, just again, bunch of numbers. Yeah. So what we are doing is, and this is an approach I recommend in machine learning. Basically, and here the data frame is very simple. I only have 1 input and 1 output, right? But when you do house sales, let me see if you do house sales. Yeah, I saw house sales here, right? Okay, this works. Right now, if your house sales data, now your X is not going to be a single column. It's going to be, let's say, I'm going to include, say, property type, bedroom, bathroom, right? All of this is going to be my X. Right? My Y usually is going to be one thing, sale price. So don't be fooled into thinking X is just one column, right? X can be 1 or more columns based on your data set. Most likely in real world data set, your X is going to have multiple columns. Y is usually 1 column because Y is what we are predicting. In this case, we are just predicting a sale price, just a number. Okay. So that kind of makes sense, guys, right? So X and Y. So I always recommend from your data frame, extract X and Y first. Because that'll kind of give you, so okay, this is my input, this is my output. Yeah, right? So now that we have this, here's my X and Y. I'm giving, so actually, scikit-learn has one nice function called train test split, very conveniently named, right? And basically arguments, you need 3 arguments, X, Y, and how much you want to keep for testing. So here, right, Cynthia is doing 20% for testing, right? So, right, so that's 0.2 basically meaning 20%. So you're doing a 80-20 split, 80% for training, 20% for testing. Okay, so let's run that. Good. So let's print out X train. Print out X train. All right. There you go. So look at the X train data. This is interesting, right? So what you will find is these are the data. What is this column? This is the index column. Remember, in Excel spreadsheet, there's a row indexes, right? 0, 1, 2, 3. Look at the X thing, right? It's completely randomized. First, it checks column number, row number 9. Then row number 8. I see the values, right? And the next one is post picked, 65. 0. You guys got that? So everything's randomly picked. That's X-train. So let me put this one here, X-train. Okay, and then let's also print X-test. Okay. There we go, right? So again, by the way, every time I run this, you will see I get different random values. See, here's, 3, 2, 5 is my indexes. Let me run it again. Completely different. Why? Everything's random. So the way the X-train and the test set splits is like it takes the data and randomly picks 80% for training, 20% for testing, right? So every time you run this, you get different results. Right, and then another thing I asked you guys to say, where was the question? Right, is split. We should inspect the data, and do you see any common elements between training and testing? Right, and you look at the data, you will not see any overlaps. See, here I'm doing row number 5 and row number 2, which you will not find in the training data. You see that? Run it again. Right, row number 8, row number 4, not found in training. Why is that? Why is it important to make sure there's no common elements between training and testing? Can anyone guess? Why do you want to make sure we don't want any common elements? What do you guys think?
You overfit.
Overfit, yeah, we are very close, very close. Any other guesses? Why don't you want the same, common data between training and testing? Because, yeah, go on.
It is trained on it. How can you test on it?
Exactly, right? Because, we don't want a model to memorize the data, right? That's as simple as this, and basically, leads to overfitting at the end of the day, right? You're right, exactly. So what we want to do is we want to keep training and testing separate, meaning model only sees the training data. It doesn't see the testing data at all. So when it tests with the testing data, it's actually new data for model. So model actually, so imagine this. Imagine you, let's say I'm, this class, I'm reviewing some Q&A, all right? Let's say I reviewed, 10 Q&A, and then the idea here is for you guys not to memorize the answer, but understand the concept. But let's say you simply memorize the answers. Like question 1, answer is A. Question 2, answer is B, right? That's what you memorized. Now, if I give this exact same question for your testing, you will do very well. But I cannot evaluate if you really learn something or you simply memorize the answers, right? So in machine learning, we want to be the same thing. So in the machine learning, we want to make sure our training and testing do not overlap. So hopefully this made sense, right? So if you look at the function, right, that's why. So you give very simple, X, Y, testing split, that's it. And every time you run this, you get different data. Now this is the problem, right? Now, I'm like, okay, so every time I run this, my data is different. So let's say I'm gonna do some experiment. Let's say I'm gonna try different models, so I'm gonna try something else. But now I cannot do this test because why? Because every time I do this, my model gets trained on different data. So this keeps changing underneath me, right? So how do I make sure I get consistent training and testing data? And there's a way to do this called random state. So random state, let's go. I always forget this. Random state, yeah, okay. So let me show you guys this. That's a number, right? Okay. All right, so I just set the random state to say, just a number 1, 2, 3. Now you see, every time I run this, right, I'll get the same data. Take it over the number, index, right, 758. 758, same data. I can do this all day, right? Can anyone tell me why this is working like this? Now, because remember, without this random state, right, I was getting right? I was getting different, you know, every time I run this, I would get different X and, you know, different Y. Sorry, different training and different testing.
It's the same starting point with the random, pseudo-random initial.
Exactly, right? So remember, this is the fundamental of in a lot of crypto algorithms and everything, right? And this is how, you know, random numbers work in the computers. So let's say, you know, in the computer, you know, it's called pseudo random numbers. So for example, let's say if we ask you guys to think of a number, right? Everyone, you know, thinks of a number, and I say, okay, add 1 to that, right? You know what I mean? Then you know what I mean, and say, think of the next number. I can bet we'll get different results from everybody. But the way computers work is like, this is called seed, right? If you set the seed, meaning sort of think of like a starting point, very loosely, not exactly, but very loosely, it's called seed, right? Let's say, if I say everyone, okay, everybody start your random numbers, but everybody use this as a seed, right? And from that point on, everybody's number will be the same. If everybody use the same seed, the random numbers after the point will be the same. So it's not really random at this point, right? You know, I can predict, like for example, if everybody uses the seed, I can predict whatever the random number I'm coming up with the same random number you will come up with, right? And you can, the seed is so simply a number, right? You can change it to something like say 10, right? You've got different, you got different numbers, but from this point on, just remember the sequence, 5, 6, 3, 1, right? 5, 6, 3, 1, see, exact same numbers, right? So every different random numbers will actually give you a different sequence, but after that point, the sequence is fixed, right?
I think this reminds me the Enigma machine, the initial,
Initial seed, exactly, right? So a lot of the computer cryptos work like this way. Remember, I mean, okay, right? The crypto is a big topic. If you go read about this, if you go read about public key and private key combination, this is exactly what's happening, right? So right? So there are random numbers at play, but the keys serve as like the initial seed, more or less, right? So to speak, exactly. Now, when you guys, here's a quiz for you guys. When you guys do look at examples, you will see a lot of the time people set the random state. The reason is they want reproducible random numbers so others can reproduce the experiment. So let's say, I'm working with you, right? We are debugging a problem, and I'm giving you the data and say, hey, I think, I have a bug. Can you check on this one? If I don't put a random in a random state, you will be able to never reproduce my experiment. Why? Unless you are really lucky and hit on the same random numbers as I have. It's not reproducible, right? Because of randomness. But if I set this, then at least you can fix this randomness. You can say, yes, it doesn't matter who runs the code, as long as they have the random state set like the same number, they are going to see the same training data and same testing data. Then we can change other things and debug. Now here's a little quiz for you guys. When you look at code, so you'll see random state often, and also most of the time you'll see people using this number 42. Anyone knows what's this number 42 means? Have you ever wondered like why is it like most people use 42?
The answer to everything.
That's right, right? So there's a little bit of a pop quiz between this. So do a search for what is 42, right? This actually comes from this really great book called Hitchhiker's Guide to the Galaxy, right? Great book, read. Anyway, so I don't want to ruin this, but basically they built this computer, and the computer can answer any question you ask about life, right? So the computer kind of keeps trying on this for, I don't know, years and years, and then it finally says, yeah, answer to everything is number 42, right? Meaning any questions, any mysteries of the life, the answer is 42. Anyway, do some reading. It's a pretty fun experiment. Anyway, but so that's why a lot of people say 42. Just a number, right? 42 is kind of like a little inside joke, right? Like, because that's the answer to everything, right? You could just take set to 0 for all I care, or just, some any number. I usually do like 1, 2, 3, 4, 5, just to kind of, tell people, yeah, this is just a number, right? Because sometimes when I do 42, people think that's like a very special number, right? It's a special number in some other context, but not really in machine learning. You know what I'm saying? As far as machine learning goes, this is just an integer. You can set it anything you guys want, right? Anyway, so now you guys know the mystery of number 42, right? But usually I do like this way, you know, it's kind of obvious, just a number. Right? All right, guys. So that's train test split. So now we kind of get an idea of, right, train test split. So same thing in house sales, right? So for example, this is just in a one attribute, one X and one Y, right? Now if you do the same thing, exact same process for the house sales. For example, you know, let's say you load the house sales, right? So let me do the X and Y. Yeah, close this here. Let me see if I can do this real quick. So what is my X for house, right? X for house sales is basically going to be house sales, right? So I'm going to say bathrooms. See, oops, sorry. See how it's auto-filling for me? Bathrooms, right? And bedrooms. And what's the other one? I'll just do one more. Say year built, right? Those are my three inputs. And Y is sale price. Okay. So print X. It's basically, okay, I think I should do double brackets. This always gets me. Yep. All right. So that's my X, all right? And what's my Y? Very simple. Do this, print X.
Do you need double brackets?
Yeah, it's basically, it's one of those pandas syntax. They expect the number of columns to be, right, in double brackets. Yeah, so right, so it gives you the right data frame. Yeah. All right, guys, so now we split the X and Y. Right? And this syntax again, you know, I mean, trust me, I mean, you know, you just saw me, right? I mean, I always get this wrong and then I cannot get it right. Yeah, it's like a little syntax, right? The little quirkiness of pandas and NumPy. But yeah, once you know it, you know it. All right, guys, so take a look at this one. See, my X is now 3 attributes. And you can just keep adding, right? You can just keep adding, and let's say I just add one more just for okay. Let's say square foot of living, right? Let's add that. All right. There you go. Now my X is right. Okay. So we have 27,000 rows, and so is that many Ys, right? Okay. Now, there's no way I can experiment this by, you know, right? Look at, you know, 27,000 rows visually. So let's do a quick split. So we can do the split again. Same thing, X train, X test. One second. Yeah, Y train, Y test. Okay. Yep. Y test is, you know, train test split. You guys get that, right? I mean, this is the same function. Train to split my X and Y test test split. Sorry, what's the parameter? Test test size and random size. Okay, let's copy this one now. Okay, just for completion, let me also get this. Okay, so done. So now if you print out, like for example, right, X train. Okay. Okay. There we go, right? So we did the split. So, you know, right, it gives me X train, Y, X test, Y train, Y test, right? And then take a look at this one. Remember, I had how many rows I had? I had 27,000 or so rows, right? Out of that, I'm doing 20% for testing and 80% for training. So it does a split, right? So you can sort of do the math, right? So for training set, I have 21,000 data points or samples, we call them. And the number of columns is 4, right? Because why? Bedroom, bathroom, right? So the shape is a great way to look at this. So it'll actually give you like the rows and columns, right? The way to read the shape. So right, shape is basically rows and columns. Okay. So, and you see my training set has 21,000, test set has 454,000, and then we print out the same thing for Y. You will see right. There we go, right? See, so one thing we have to make sure, right? Training and training has to match. Training, see, numbers match. Test, numbers match. Okay. And the Y train, there's no columns, we just call number of columns is 1, right? So, so that's why, right? And we are predicting. So they're going to make sense, okay? Train, test, split. Now we understand what's the theory behind this, right? And just one line of code, basically, right? And you can play around with this. Let's say, let's say you want to do like 70-30 split, right? Sure, make this 0.3, right? Because y 0.3 times 100, right? And then you get the different splits. Now, what's the right number here? Nobody can tell you. So nobody can argue with you. It should be 70-30 or 80-20. It's just we all agree it should be more towards training. So a lot of the time, people kind of you can just choose one, and as long as you get decent results, nobody can argue with you. Yeah. Good, guys. So is this clear? So this is basically the scikit-learn. Any questions on this one, guys?
Yes, when you want to do the cross-validation out of that, you take the, out of the 21,000, you take the first 21,000 divided by 5.
Oh, so okay. So when you want to cross-validation, so remember for cross-validation, you can give the entire data because what am I doing here? Because cross-validation will split the data for you automatically, right? So here we are doing the splitting, training and testing split on our own, right? For cross-validation, you can give the entire X because as you can see, right, cross-validation will actually split the data for you automatically. Does that make sense? Yeah. So we don't have to split. We don't have to pre-split before cross-validation. We just give the entire data, and cross-validation will take care of everything for us. Yeah. Good question. All right, guys. So let's see. So question is like, yeah, scikit. Yeah, so great question. So for machine learning, the question was, is scikit the only library or can we use like keras or TensorFlows, right? So in Python, in machine learning, scikit is pretty much the go-to library. Machine learning, remember? Keras, TensorFlow, they are deep learning libraries, right? So they have very different underlying implementation. So if you're doing classic machine learning that we are doing right now, scikit is the way to go. Yep. All right, guys. So let's see what else we have done here. Let me quickly run through this algorithm real quick. So last time we looked at what is machine learning, right? What is right? What is deep learning? Some of the differences. I want to quickly point you guys to some of the algorithms, and that's what this week we are going to look at, right? This week we are going to look at linear regression algorithm. So if you look at the algorithms, right, how machine learning algorithms. Again, this is part of your machine learning, your slide deck number 7, machine learning primer, right? So here's a nice algorithm chart I provided for you guys to understand what algorithms we are going to be covering. So algorithm predominantly fall into 2 categories, supervised and unsupervised. Yeah. So supervised learning basically meaning we train the algorithm, then the algorithm predict. So under supervised, there are two main categories, regression and classification. So what is the regression? Regression is basically trying to predict numbers. So predicting house prices, predicting stock market, predicting the temperature, right? I'm predicting a number. And these are some of the algorithms we will use, right? Linear, polynomial, ridge, right? So we look at linear regression this week. Classification is basically, you classify things as one or the other. For example, if I show you an email, you're classifying the email as spam or not spam. If you see a cat or a dog picture, you classify it as a cat or a dog, right? You're classifying, right? And these are some of the popular classification algorithms, right? So, and the reason is sort of the chart, I really like the chart is kind of, if somebody says, I'm using SVM, you can see, okay, what is SVM? Oh, interesting. Okay, that's a classification algorithm that is supervised, meaning it's trained. We train the algorithm, right? And if somebody says we are using random forest, we know, okay, that's interesting. That's a decision tree algorithm that's supervised, right? Now, the reason decision trees, I cannot put the decision tree as a separate category here and the subcategory is because the trees can do both regression and classification. That's why I'm gonna put them as a third category, right? Because under supervised, basically we have only two categories mainly, regression and classifications, right? So since trees can do both, I can put them in its own category. Right? So let's look at these, these algorithms very quickly, right? Again, I'm gonna look at unsupervised and unsupervised real quick, guys. Okay. So supervised algorithm is what we are going to look at going forward. Sorry, was that a question?
Yeah, I wanted to say that that's why we should have some semi-supervised or semi-unsupervised learning.
Yeah. So I mean, we actually have semi-supervised learning, but usually I don't see this quite a bit. It's like a very special use case. So that I have it here, but most of the algorithm we are going to be using are in these two categories. Yep. Okay.
One more question.
Yeah.
Are we going to review all these models that you show in that table in this class?
Yes, we are going to go through, we're going to learn, we learn most of these algorithms that are highlighted here, right? Some of the algorithm, okay, I'll leave it to you as homework. We are going to go through these popular algorithms, right? These are the popular algorithms we do use in machine learning, exactly. So now that we are at a position, we understand the basics, right? We are going to start looking at algorithms. Yeah. So when somebody says, I'm using a supervised algorithm, what does it mean? It basically means we are training the algorithm on some data, and then the algorithm predicts on the new data. That's it, right? So training and then prediction. So what are the algorithms that we use in supervised? Basically, we have two main types, right? Classification and regression. What is classification? Classification is like, you're categorizing things into groups, right? Spam or not spam, fraud or not fraud. And regression is basically predicting a number, house price, stock market price, whatever, right? That's it. So let's say want to do a stock market prediction algorithm. Remember, I need to train my algorithm, right? So what we do is we get some past stock market data, right? And we train the algorithm. And as you can see, I'm basically splitting the past data into training and testing already, right? Because why? Because I want to test my algorithm objectively. If I used up all the data to train the algorithm, then I have nothing left to test with. And now you guys understand why we are splitting the training and testing, right? Because we don't want the model to cheat. So I get some data from stock market data, I train my algorithm, right? The training data and testing data, right? And then the model try to predict. Right? So the classification example, same thing, right? Let's say I'm building a classifier, same thing, right? I'm training the classifier, and here I have mixed data coming in, and the classifier will put them into the right category. Like for example, this could be spam emails or not spam emails. This could be credit card fraud credit card transaction, and this is like a good credit card transaction, right? I'm classifying one or the other. Right? So these are the examples of classifiers, right? For example, when you do like a medical biopsy, does the cell has cancer or not? Right? Is a credit card transaction fraud or not? You're classifying, right? So it's kind of saying yes or no, right? Now, so that's training and prediction. Then there's another category called unsupervised, right? So unsupervised, there's no training. we give the entire data to the algorithm and then ask the algorithm to pick out patterns. So the most common use case in the unsupervised is like clustering. So here, right? So what is the clustering? Clustering is basically trying to find patterns in the data. Let me show you an example. So let's say I show you this data. And I say, do you see any patterns in the data? You say, sure, I see 3 patterns, right? I see like a little in this group, this group, this group. But see, you may not know what each of the groups means. Right. So for example, let's say, in my example, the one I used is, I grouped alcoholic beverages, right? So like red wine, like red wines, they share similar properties together. So they tend to cluster together. White wine, different, pretty much all the white wines have more or less same properties. So they cluster together. Beer has different properties. They cluster together. But as an algorithm, when you're doing clustering, right? You don't know this is red wine. You don't know this is beer. You simply see the groups. Because why? You see the similar characteristics. And that's why we don't need training, right? Because all I'm doing is I'm picking out patterns. Does that make sense, guys? All right? So sometimes people get confused about clustering and classification. It's not. Clustering is basically finding patterns. Classification is like the next step, usually, right? Once you find a group, okay, what is this, right? Is it red wine, white wine, or beer, right? That's the next step. But the first step is finding groups. And that's called clustering, right? Now, this is a 2-dimensional data, right? Now, x-axis and y-axis. So, our eyes can figure out patterns very easily, right? What if I had another dimension, like x, y, and z-axis? So now we have 3-dimensional data, right? Then it's kind of, it's kind of hard for us to visualize. What if I had 10 axes, like, x1, x2, x3, x10, 10 axes? Then, I cannot visualize it, right? But that's where the algorithms come in, right? Because the math is the same math. Doesn't matter how many dimensions we have, right? Whether you have 2 dimensions, 20 dimensions, it's the exact same math. More complex calculation, but, math is the principle is the same, right? So that's why we look at clustering. Okay. Is that gonna make sense, guys? Right? Clustering algorithms, right? So here's a use case. And if you say, okay, that's great, but what do we use it for, right? So here's a use case for clustering. So imagine you're analyzing web traffic. Let's say, you're analyzing some, web traffic to your online shopping network or something, right? Let's say most of the traffic kind of falls into this category, and suddenly you see a different traffic coming up. So, right, and algorithm will highlight and say, hey, I'm seeing a different pattern here. Then you can go and investigate. So what the algorithm will do is sort of cluster. I will say, hey, unusual traffic together. So it's called anomaly detection.
May I ask, Suji?
Sure.
In clustering, I think the intelligent part of a human is to identify what features are going to be included into the clustering for classification.
Yep.
In order to make something more meaningful. So just to include all the features immediately, it could be more confusing than actually giving a hint of what's happening.
Yes. Yep, exactly. And this is what machine learning is about, right? I mean, machine learning, like for example, right? When I show this picture to you guys, this is a 2-dimensional data, right? So I'm asking the algorithm to cluster using only 2 properties. I don't know, like let's say something like alcohol content and I don't know, fizziness or something, right? Something like just 2 properties, right? But it doesn't have to be 2 properties because it's an example. But like as you mentioned, this can be multiple attributes. Let's say somebody gave you data that has 100 features, 100 columns. Which columns are we going to supply to the machine learning to to look at, right? I mean, you can pretty much give all 100 columns, but then you're kind of adding a lot of noise to the data, right? So that's a human part of this machine learning, right? We actually kind of tell the machine what features to look at, and based on this, they will come back with a grouping. Yep, you're right, absolutely, right? So that's why the human in the loop right now, like as humans, we actually trying to understand what features are important and feed that to the algorithm. And even that can be automated to an extent these days, right? And we'll see those a little later. Yep. that gonna make sense? Guys? Clustering use case, and one of them is anomaly detection, right? So another question is basically, is the classification always mutually exclusive? Like for example, when you classify data, is it always like A, B, C, D, like one of those, right? Or can it be like, can it be like a combination of, right? Typically, I've seen them as exclusive. Like when you get input data, right? Input comes in, the classifier is going to give you either A, B, C, or D, right? And we usually end up picking one. Okay, we say, okay, input is basically A, right? Now, there are classifiers that can do what we call multi-classification. For example, what they do is they give you a probability like this, right? They give something like, they will say, input is X, so it'll say, I think this is 60% A, right? Maybe 30% B, and then 7% C, and 3% D, right? So what they do is they give you like a probability, and if you add up all the probabilities, it should add up to 100%, right, or 1. So there are some classifiers out there, they are not going to give you like A, B, or C, or D, they will give you probabilities, right? So they will say 60% A, 30% B, right? Something like this. So here, is a pretty clear winner, right? I mean, A is a clear choice. So we can say, okay, this is most likely A. What if the algorithm says this is like, 45% A, right? 48% B, and then the remainder split in C and D, right? Now, it's not a very clear winner, right? Because they're kind of more or less equal, right? So now, the algorithm is ambiguous. And that happens too, right? Usually when we do classifications, you get pretty clear-cut answers, right? But there are scenarios you can get into where your answer is kind of ambiguous. Then, you had to kind of figure out, right, what to do, right? And sometimes you can ask users for help, for example, right? And this you may have seen in credit card, like if you have credit card, fraud system, right? And most banks now use it. Let's say you swipe your card, they can pretty much determine if this is fraud or not, and they can stop the fraud right away. But sometimes they cannot make a decision on their own. Then what they will do is they will send you a text, right, saying, "Hey, did you really make this purchase?" Like say reply yes if you did, and no if you didn't. So what are they doing, right? Because the algorithm is now cannot understand if this is fraud or not. So they're asking your help. So they can be sending a text message, or your app, something pops up on your app, or sending an email or whatever, right? And asking your help. Then you say, yes, this is a fraud. I didn't make the purchase, right? Then they can go ahead and block the transaction. Anyway, so there are a lot of ways you can deal with this when there's uncertainty. Right? Hopefully that made sense. Good question. Okay, so clustering. Oh yeah. So what are the clustering applications? We'll see this quite a bit. For example, when you're doing when you do DNA analytics, right? Remember when you want to group people with a similar DNA, similar mutations, right? Things like that. Let me show you an example. Google News. We go to Google News, right? So let me show you an example. So we go to news.google.com. So so here's the main story, right? And for each story, there are multiple articles. Right? And if you click on the view full coverage, you get all the articles for the topic. I see how they're segmenting like news stories, tweets, right? Everything, right? So what they are doing is they are basically clustering. So they're reading all the news stories, all the tweets, and they're clustering. Okay, they'll say, okay, all these stories basically are talking about this subject, right? So that's pretty cool, right? And this is called clustering. So they're kind of clustering similar stories together, right? So for example, right, and when you click on the right, more coverage, you will see, and this is a classic case of clustering. So what they're doing is they're aggregating all the news stories, and they're kind of right, and they're kind of clustering under the same story. They're from different outlets and right from different people in the tweets and whatnot. Yeah. So okay. Right. So that's a clustering algorithm. All right. I'm going to zip through real quick. I'm coming up to the end of the class. And this is another use of clustering. I don't know if you guys have seen this. Here in US, I see quite a bit of this in, say, you go to like a Walmart or Target store, right? when you walk down the aisle, sometimes you will see they are like this, they are called islands. These are like little bins of goodies, right? Set up in the middle of the aisle, and most likely they are something different, right? So I remember walking down a cereal aisle in one Walmart, and in the middle aisle, they actually had like an island set up with the with the LED light bulbs. So what's the link between an LED light bulb and cereals, right? Nothing, right? However, as it turns out, I needed some light bulbs. I picked up some light bulbs, right? So what they're doing is they're analyzing what people are buying together, and they're trying to put these items together. So I do my grocery shopping in a Safeway close to my house. So usually when I like, for example, when I go to buy milk, right next to the milk, refrigerators, they actually have a section with like bananas. Right? But it's like a small section, right? Just a small section of bananas. The actual grocery section is on the other side of the Safeway, right? But when I usually go to buy milk, I sometimes pick up some bananas too. I go, oh, cool, right? So I need some bananas, I'll just pick some up. So how are they putting these items together? Think about this, right? Because what they're doing is they're analyzing the shopping basket, what people are buying together, and they're trying to figure out what people are buying together. So clustering, right? Go back to the original diagram, right? I'm trying to understand which items are in the shopping basket and how they cluster together. So if Safeway kind of figured out, people who buy milk also tend to buy bananas, right? What they will do is they will just put a little bit of bananas right next to the milk aisle, right? So when you're going to buy milk, you just, oh, it's right there, right? They're kind of upselling you, right? So you went to buy milk, but now you left Safeway with milk and bananas. Right? It's good for them, right? Because they sold you more items. so next time you go through a supermarket and you see something in the island, and there's a completely unrelated items, think about this and say, how did they figure this out, right? How did they figure out, why did they put this item in this aisle? So it's not random, guys. It's there's a lot of algorithms at play, right? What they do is they analyze all the shopping basket data and then figure out what people buy. So Walmart basically published their shopping cart analytics. You can look at the link here. So they basically clustered their shopping basket like this: pharmacy run, right? You simply just let's say you have a cold, just you directly went to the pharmacy, you bought some whatever, right? Some cold medicine, and that's it. Just went to buy grocery shopping, right? Or just went to buy like a gallon of milk. That's it. Right? Just you order milk, just pour the milk, right? What do you guys think this is? Right? This category. Right? What do you guys think was in the shopping basket? Can you maybe guess? Right? So you should read this paper, right? They made some pretty fun discoveries. Anyway, so when you look at what people are buying together, then you can put the items together to increase sales. Again, clustering, right? What we're trying to find is they're trying to find what are the buying patterns. Pretty good, right? So this is important, and that's the reason I'm spending time with you guys. Like when somebody gives you a problem, somebody says, okay, I'm going to give you weather data. Can you predict tomorrow's temperature? What kind of an algorithm we are going to use, right? So you should be quickly able to kind of look at this. Let me sort of quickly go to the advanced thing, right? And say, okay, in all the algorithms I have, okay, I'm going to predict a number. Okay, so that's a regression. So that's supervised, meaning I need to get some data for training, and I can use these algorithms formatting, right? If somebody says, okay, we are getting we are doing like website traffic analysis. I need to classify my clicks as humans or bots, right? So what are we doing? So now at this point, we are doing classification, right? Because I'm classifying a click to see if it's a bot or a human. So again, these are the algorithms we are going to use. So you guys understand, right? So you need to be able to map the problem to a domain. And then from there, so for example, right here, you see to do classification, I'm showing you 4 algorithms. Now, how are you going to pick one of these 4 algorithms? Just like before, remember, this is what I showed you guys in the cross-validation example, like this. You're going to try 4 algorithms and do like a little cross-validation and then see which algorithm gives you better results, right? There's no mystery. You don't have to, there's not like a magic formula that tells you, okay, yeah, for this data, you should use SVM. You simply try them all out and pick the best winner. Right? All right, guys, good. So I'll stop here. We are going to look at the algorithms, right? So the first algorithm we are going to look at is linear regression. So I updated my my curriculum here again, so you can look at this. Where's my path? One moment. Right. So this week we are going to look at linear regression. Okay, so you guys have done through all of this, right? Machine learning, scikit, we all done. So if you're kind of catching up, please catch up. And this week we are going to go into linear regression, same thing. So this time I'm going to give you some videos. This is a really great video series to understand. So you can watch this, right? And it'll give you a pretty good sense of what linear regression is. And again, same deal, right? Reading materials and then basically checklist, right? So you should be able to kind of so treat this as a quiz, right? To say, okay, do I understand what SSC means, right? Do I understand what R-square means? Yeah, and then exercises. Okay. By the way, did we go through the errors, the sum of squared errors and all that in the last session? Do you guys remember? Did we sort of go through these different error metrics? If not, I will cover them in the next section. Yep. Yeah, I need to sort of review the video because I can't remember if I did this or not. But if not, no worries. We'll do it next week. All right, guys. All right. So that's it. So like I said, we are looking at our first algorithm. So this is exciting, right? So now we're going to look at our like a very simple algorithm, which is linear regression. And from here on, we'll start looking at the algorithms, right? Other algorithms. Good, guys. That's it. So we are done for today. If you have any questions, you can feel free to stick around. Otherwise, I will keep an eye on the mailing list. I will send you guys the assignments and go forward. Yep. All right, guys. Thank you so much.
Thank you.
Thank you.